Welcome to everybody for one more session of the Logical Universalist webinar. We are still waiting 1 or 2 minutes before starting and trying to fix some technical problems. So today we'll have a talk by Norihiro Kamide from Tokyo University in Japan. Arnon will be the chair of the session, but he is fixing some problem with his microphone. Let's see. Meanwhile, I would like to ask some questions to discuss a bit about logic in Japan with Norihiro Kamide, because before each talk of our webinar, we have presentation of logic group. Logic research in the country or in the field of the researcher. So Norihiro, if you can first tell us a bit about how did you study logic in Japan? I mean, which kind of department, if it was in the mathematics department, where, how did you learn logic, if I may say, in Japan? Where did you learn logic? What kind of class? Because today your lecture will be about proof theory and it's related with Paraconsistent logic. So how did you learn these things? Did you learn this kind of tools, techniques in Japan or by yourself? If you can say a few words about that.
In my study?
Yeah.
In Japan, there are some logic groups, but I think there are no philosophical logic group. There are some mathematical logic group, such as axiomatic set theory, model theory, and reverse mathematics. And my supervisor was Hajime Ishihara, who is a mathematician, and his major is constructive mathematics. And in Japanese group, the characteristic of Japanese group, in a sense, logic is not a popular science in Japan. There is no tradition of logic.
I see. So logic is not popular in Japan. Yeah, we hope things will change in the future. But how do you explain that logic is not popular in Japan? You have a
it's difficult to explain. But some famous researchers, such as Gaeshi Takeuchi, who is a proof theorist.
Yeah.
And yes, the Professor Toshiyasu Arai, who is a proof theorist, his major is proof theory. And another famous logician is Hiroaki Ono,
Yeah, yeah.
who is also one of my supervisors.
But Hiroaki Ono is retired now, no? He's not.
He's retired, but yes, and my supervisor Hajime Shihara will be retired next, perhaps next year.
I see.
Next year, March, last of March.
So you did your master thesis and PhD at the Japan Advanced Institute of Science and Technology. That's right.
Yes. Joist Hokuriku, Japan Advanced Institute of Technology.
So as far as I understand, yeah. Please.
Yes, there is a logic group in Joist Hokuriku. I'm a graduate of Joist Hokuriku.
So you are still in touch with the people at Joist?
Yes, yes. There are some logician or mathematician in Joist.
Okay. And as far as I understand, Joist is located in Ishikawa, that's right?
Ishikawa, yes. Kanazawa.
Yeah, Kanazawa. I have been there. It's a very nice place.
Yeah.
It's right here. And so the Joist is one of the most important institute for research in Japan, no?
Yeah.
It's a very, very important research institute. So it's good to know that still that there are some people working in logic there.
Yes, mainly studied for constructive mathematics and reverse mathematics. Now in Joist. Studied in Joist people, researchers.
And then what about J.Z. Takuchi? Because he's one of the most famous Japanese logicians. He's not alive now, but I mean, he was famous working in proof theory. We have here one member of the Editorial Board of the Studies of Universal Logic, Join Lee. Can you listen to me, Join Lee? Because he did his Join Lee is from Taiwan. He did his PhD with Takuchi in the United States. But it was hello?
Huh.
I don't know if he listened to me. I see him on the list.
Sorry?
I am talking with Jun Lee, who is here, but I don't know if he's listening to me.
Yes, can you hear me?
Yeah. Maybe you can show up. Yeah, okay, thank you.
Yeah.
So maybe you can say a few words about J.Z. Takuchi. How did you, you were in touch with him, but in the United States, not in Japan?
Okay, I think I actually went to US to study, and because I just look at, there's a very thick handbook of mathematical logic.
Yeah.
And I just, when I study as undergraduate student, I just browse the book and find some, maybe say some name logician there, and I actually don't know much about logic. Anyway, but I think before Geisel retired, he actually tells us some of his story. Okay, so I think he graduated about in Tokyo University, got his PhD, and it's about 1957 or 58, maybe 58. And at that moment, that's after the Second World War, and the life there is very tough. So he got invitation by Gödel Okay, so after he got in there, he go to the US. I think it's something like 1961. So he visited the IAS, Institute for Advanced Study, and then he traveled a lot among US, and finally he arrived at the University of Illinois at Urbana-Champaign, something like that. So that's roughly the story like that. And he also told me that he actually studied Gentzen's paper by himself. Okay, so he became a proof theorist by his own. So there's something like that. And when he arrived at US, actually his Dutch is better than English. He said he can watch the German movie and have a better understanding, something like that. Yeah. So I think he also told me that his thesis advisor didn't give him many help. Actually, he studied by himself. Because he studied Gentzen's paper, something like that. Yeah.
But so you did your PhD with him?
Yes, in US.
All right, good.
And I was there among 1991 till 1996, and he retired at 1996. Yeah, and because he had some Geisli Takeo, he retired from University of Illinois at Urbana-Champaign, and in 1996, because I think he had some health problem, some health concern, so he retired. And yeah, and before that, he just told us some of his own story. Yeah, so that's what I heard from him. Yeah.
But then he never came back to Japan.
I think his daughter is one of his daughter is in the where Baltimore or somewhere. I mean, in the orchestra. I forgot the place. So I think at the moment he's something like lived half years in US and half years in Japan, something like that. He moved back and forth. And he also told us the story that when he left Tokyo, he sold his house. But after that, when he moved to US and he earned the money, he cannot buy back the same house because I mean the house become very expensive in Tokyo. He told us some story like that. Yeah. And I think, but after that, I think in his late year, and I think his health become not good. So I think maybe after 2010, he stayed in Japan, and I think he passed about, I forgot the exact year, something like 2018 or 17, I forgot. And he had a very, very, very high age, something like 95. Yeah. I think his health condition, he lived really very long. Yeah. Yeah. But I also heard that in the very last few years, he is not able to attend those logic seminar or some discussion, and it's kind of pity. Yeah. Okay.
Thank you.
Mm-hmm.
And so, Norihiro, how did you study, I mean, the Gentzen systems? I mean, by yourself, like Takechi, or
myself.
you had class? By yourself?
Myself, 20 years, 20 years. From my PhD thesis from now about I studied about 20 years.
Okay, so I think we will start the talk, but I'm not sure that Arnon succeeded to solve his problem with the microphone. So no, we can still, no, didn't succeed. So well, what about you, Jun Lee? Maybe you can you can act as a chairman because you are here and present Norihiro Kamide. You're ready for that?
Okay, okay, I will serve as a backup. But anyway, I think Professor Avron, I think he can also send some message by chat, maybe.
By chat, yeah,
okay.
maybe.
Yeah. But I mean, that's just some typing.
Right.
But anyway, I would like to help, and so let me serve as a backup here.
Okay, thank you.
So so today we are going to have Professor Norihiro Kamide to speak about this talk, unextended paradefinite logic combining conflation, paraconsistent negation, classical negation, and the classical implication, how to construct nice Gentzen-type sequence calculi. Okay, so you can say now.
Thank you. Please wait a minute. It is okay?
Yes, I can see everything.
Okay. Sorry. Okay. The aim of this study is to construct a nice logic Gentzen-type sequence of calculus that has some good properties and theorems. In this talk, we introduce a new logic, Eplc, which has an extended paradefinite logic with connectives as addressed here. And we prove some characteristic properties and theorems for this logic. Using these properties and theorems, we can obtain some nice Gentzen-type sequence calculi for the logic. The contents of this talk are structured as follows. First, I will present the results and the overview of this study. Second, I will present some motivations and the backgrounds of this study. Third, I will introduce a sequence calculus and the semantics of the proposed logic. Fourth, I will show the main theorems for the logic. Finally, I will conclude this talk and address some future works. Let's move on to the first section. I now present the results and the overview of this study. In this study, we introduce an extended paradefinite logic with classical negation, Eplc, as a Gentzen-type sequence calculus. Eplc has connectives of conflation, paraconsistent negation, classical negation, and classical implication. Eplc is a conservative extension of Bell-Napdhan logic and proportional classical logic. Bell-Napdhan logic is also referred to as first-degree entailment logic, or Dan-Bell-Nap logic. The conflation connective is regarded as the logical counterpart of the conflation operator equipped with the algebraic structures of bilattices. Eplc is also regarded as a modification of Avron and Zamansky's ideal over the paradefinite logic known as 4cc. This logic is also regarded as an extension of De and Moll's extended Bernard-Avron logic with classical negation, known as BD+, and Avron self-extension for-value paradefinite logic, known as SE4. 4CC is regarded as a variant of the logic of logical lattices, and it has also been studied by myself and Yonizawa using an alternative Gentzen-type secant calculus called EPL. BD plus was shown to be a conservative extension of SE4. Namely, SE4 is the classical negation-free fragment of BD plus. We proved the completeness, elimination, and dissolvability theorems for Eplc using Maihara's decomposition method. We also proved some theorems for embedding Eplc into Gentzen's LK for classical logic. We also proved the self-extensional property for Eplc. Maihara's decomposition method was originally used to simultaneously prove the completeness, elimination, and dissolvability theorems for LK. In this study, we also obtained an embedding-based proof of these theorems. We obtained the admissibility of the following rules of contraposition, inversion, and negative symmetry in Eplc. The tilde and minus symbols are paraconsistent negation connective and conflation connective, respectively. The admissibility of the contraposition and inversion rules are crucial for showing the self-extension property of Eplc and other logics. The obtained properties are regarded as characteristic properties for Eplc, as they do not hold for typical paraconsistent logics with implication. Using some of these characteristic properties, we can obtain some alternative simple Gentzen-type secant calculi feature theorem equivalent to Eplc. Prior to address motivation for developing Eplc, we give an explanation on motivation for studying a specific type of non-classical logic. The classical negation-less fragment of Eplc is regarded as a specific type of paraconsistent logic, which has multiple names. It is called Paradefinite Logic by Areli and Avron, and Non-analytic Logic by Da Costa, and Paranormal Logic by Vezio. Regardless of its name, Paradefinite Logic incorporates the properties of both paraconsistency, which rejects the principle of explosion, and paracompleteness, which rejects the law of excluded middle. Paradefinite logic is known to be appropriate for handling inconsistent and incomplete information, and is also useful for handling indefinite information. Areli, Avron, and Zamansky's ideal for valid paradefinite logic 4CC and Nelson's paraconsistent for valid logic N4 are typical examples of paradefinite logics. Eplc is regarded as a modification of 4CC. As mentioned, Eplc is an extension of Avron's self-extension for valid paradefinite logic SE4. SE4 has a self-extension property, which is known to be a significant meta property of logics that standard logics have. Actually, SE4 was shown to be the unique self-extensional extension of Bernard-Avron logic by adding implication. Through the study of my paper on logical universalities, I understand that SE4 is a natural and nice extension of Bernard-Avron logic, and is also a natural subsystem of classical logic. This will be explained in the final section of this talk. A paradefinite logic with this property was referred to as self-extensional paradefinite logic. The discovery of self-extensional paradefinite logic with implication is known to be a significant issue. This issue is significant because one of the main drawbacks of many of the well-known paraconsistent logics, including Nelson's N4, is that they lack this property. Concerned with this issue, it was proved by Avron and Bezier in 2017 that no three-valid paraconsistent logic with implication can be self-extensional. This result is a generalization of the results by Bezier in 1994, where it was shown that the three-valid logics LP and J3 have no self-extensional property. By contrast, it was proved by Avron in 2017 that there exists a unique self-extension of three-valid paraconsistent logic within the language: conjunction, disjunction, and negation. The results addressed above raise the question of whether there exists four-valid self-extension paradefinite logic with implication. Concerned with this, it was addressed by Avron in 2020 that SE4 is a logic of this type. Actually, as presented by Avron in 2020, SE4 is a unique self-extension extension of Bell-Napton logic by adding implication. It was observed in a previous study that SE4 is a classical negation-free fragment of D and Mori's axiomatic extension BD plus of Bell-Napton logic by adding classical negation and classical implication. This also means that BD plus is a conservative extension of SE4 obtained by adding classical negation. The essential equivalence among the following philosophically plausible logics was observed by D and Mori in 2015. D and Mori's extended Bell-Napton logic BD plus, Bezier's four-valued model logic PM4N, the Zaitsev paraconsistent logic FDEP. Another system which is essentially equivalent to BD plus is Mendez and Robles' PL4. Based on this equivalence, the fundamental aspects of these logics were elucidated. This figure represents the relationship among the logics under consideration. Eplc is the proposed logic in this study. BD plus is D and Mori's extended Bell-Napton logic with classical negation and classical implication. CL is classical logic. SE4 is Avron's self-extension of four-valued paradefinite logic. And 4CC is Ariel, Avron, and Zamansky's ideal four-valued paradefinite logic. The 4CC has a conflation connective, but the classical logic has no conflation connective. Thus, strictly speaking, it is not regarded as a subsystem of CL. SE4 and 4CC are not logically equivalent. Actually, 4CC has no self-extension property, but SE4 has this property. A detailed comparison will be explained soon. Let's move on to the next section entitled Motivations and Backgrounds. I now present the motivation and the backgrounds of this study. A motivation for developing Eplc is to obtain a good conservative extension of both paradefinite logic and proportional classical logic that is philosophically plausible and useful in computer science. Such a nice logic may be useful in computer science application areas that use both paraconsistent and classical reasoning mechanisms. As in such application areas, we must appropriately and simultaneously handle indefinite information and definite information. Furthermore, extending paraconsistent logic by adding classical negation as conserved in such a logic is known to be an important issue for non-classical logic. Another motivation for developing Eplc is to obtain nice Gentzen-type Sequent calculi that have some good properties and theorems, such as the self-extension property and the elimination, completeness, disability, and embedding theorems, and can obtain simple proofs of these properties and theorems. To construct such a nice logic, we have to consider compatibility issues for combining conflation, Paraconsistent negation, classical negation, and classical implication. There are three issues which are addressed in the next slide. Issue 1. Is there an extended combined paradefinite logic that has the self-extension property and the admissibility of the contraposition, inversion, and the negative symmetry rules? This issue, especially for self-extension property, is known to be a crucial issue for paraconsistent logics. Actually, it is well known that the self-extension property and the admissibility of the contraposition rule do not hold for typical paraconsistent logics with implication, such as Nelson's paraconsistent four-barrel logic N4, as well as the above-mentioned paradefinite logic processes and the logic of logical bilattices. Issue 2. If there is such a logic, then how can it be constructed? Issue 3. If such a logic is constructed, then how can be completeness, elimination, dissolvability, and embedding theorems be proved? These issues are settled in Eplc, and some nice Gentzen-type Sequent calculi are obtained for Eplc. In addition, we have to mention that these issues have already been partially settled in BD+, except for the item concerning the explicit addition of the conflation connective. In order to compare Eplc and other related logics, we address a detailed explanation on the construction of Eplc as follows. Eplc has a conflation connective and the paraconsistent negation connective, the classical negation connective, and the classical implication connective. The negated implication inference rules of Eplc correspond to the new axiom scheme of the form. This axiom scheme is equivalent to De and Omori's characteristic axiom scheme of the form, using BD+ by assuming the new axiom scheme, as considered implicitly in 4cc and EPL. The conflated implication inference rules of Eplc correspond to the new axiom scheme of the form. This axiom scheme is equivalent to the axiom scheme of the form by assuming the new axiom scheme of the form. We now give some comparison among Eplc and the previously proposed logic 4cc, EPL, and BD+. It was shown by myself and Zoad that 4cc and EPL are logically equivalent. This was shown by Yonizoa. Compared with Eplc, the logic EPL has the logical inference rules that correspond to these axiom schemes instead of those in Eplc. And this axiom scheme is a characteristic axiom scheme for Nelson's N4. And this axiom scheme is a characteristic axiom scheme for connective logic. I'm replacing the conflation connective by negation with negation connective. It is a characteristic axiom scheme for connective logics. Owing to these logical inference rules of 4cc and EPL, we could not show the self-extension property and the admissibility of the contraposition and the inversion rules, although the admissibility of the negative symmetry rules hold for 4cc and EPL. Compared with EPL and 4cc, the logic BD+ has no conflation as conflation connective as a primitive connective, and no axiom scheme of the form, which is subsumed in EPL and 4cc. Thus, BD+ and 4cc are different logics, but are closely related to neighbors. We believe that Eplc is a nice modified and combined extension of both 4cc and BD+. Actually, Eplc is regarded as a natural extension of BD plus by adding the conflation connective. Next, we explain the ways of proving the main theorems for Eplc. The unified semantic proof method by Rahab and Avron proposed in 2013 for proving the completeness and culmination theorems for Gentzen-type secant calculus or 4cc and other Gentzen-type secant calculi for a wide class of non-classical logics seems sufficient for Eplc, although it has not yet been investigated. However, proving the dissolvability of Eplc is insufficient for this method because it is not clear how a decision procedure can be given for Eplc by this method. Thus, in this study, we use Maillard's decomposition method for simultaneously proving the completeness, culmination, and dissolvability theorems for Eplc. To use Maillard's decomposition method smoothly, we construct Eplc as an appropriate set of initial sequence and logical inference rules. In this study, we also use the embedding-based proof method used in the previous studies for proving the completeness, culmination, and dissolvability theorems for the underlying logics. This method gives us an alternative unified proof of the main theorems for Eplc. Okay, let's move on to the next section entitled Secant Calculus and Semantics. In this section, I will introduce the Gentzen-type secant calculus Eplc and the semantics of Eplc. First, the formulas of Eplc are defined as follows. Formulas beta of Eplc are obtained by the following grammar, assuming P represents a proportion variable, where tilde and minus symbols are paraconsistent negation connective and conflation connective, respectively. The logic Eplc is defined as a Gentzen-type secant calculus. An expression gamma implies delta is used to represent a secant where gamma delta are sets of formulas. The gamma delta sigma are used to represent a set of formulas. This is the definition of Eplc. The initial sequence of Eplc are of the form. The structural inference rules of Eplc are the same as those of Gentzen's LKM, although the contraction rules are omitted here because the sequence are formalized as a set-based sequence. One of the characteristic points of Eplc is the form of negated and conflated initial sequence. These initial sequence for proportion variable extend to those of formulas. The fourth and the fifth initial sequence correspond to the principle of quasi-explosion and the law of quasi-excluded middle, respectively. The non-paraconsistently negated logical inference rules of Eplc are of the form. Namely, these rules are the same as those for LK. The negated logical inference rules of Eplc are of the form. The negated conjunction and disjunction rules correspond to De Morgan laws. And the negated implication rules correspond to one of the characteristic axiom scheme of Eplc. In addition, the negated classical negation, negated paraconsistent negation, and negated conflation inference rules are of the form. For example, these rules correspond to the characteristic negated classical negation and negated conflation axiom schemes. We have to add some conflated logical inference rules as well. The conflated logical inference rules of Eplc are of the form. For example, these conflated implication inference rules correspond to one of the characteristic axiom scheme of Eplc. In addition, the conflated classical negation, conflated conflation, and conflated paraconsistent negation inference rules are of the form. For example, these rules correspond to the characteristic conflated classical negation and conflated paraconsistent negation axiom schemes. These proportions generalize the initial sequence for proportion variable to those for formulas. Namely, we can use the formula-based initial sequence in Eplc. Next, we define a semantics for Eplc. We use the set of classical truth values. We also consider the set of all negated and conflated proportion variables. Then, a paraconsistent variation B asterisk is a mapping from the union of the set of all proportion variables to the set of all negated and conflated proportion variables to the set of classical truth values. Furthermore, we need the following condition. This condition corresponds to the initial sequence that corresponds to the law of quasi-explosion and the law of quasi-exclusive middle. The paraconsistent variation B asterisk is extended to the mapping from the set of all formulas to the set of truth values by the following clauses. The clauses from 1 to 4 are the same as those of classical logic. The clauses for negated conjunction, negated disjunction, negated implication, negative classical negation, negative paraconsistent negation, and negative conflation are as follows. For example, this clause corresponds to the characteristic axiom scheme of Eplc. The clauses for conflated conjunction, conflated disjunction, conflated implication, conflated classical negation, conflated conflation, and conflated paraconsistent negation are as follows. For example, this clause corresponds to the characteristic axiom scheme for Eplc. The notion of Eplc validity is defined as usual. This proportion generalizes the mapping condition for proportion variable to that for formulas. Using this proportion, we can show that the following characteristic formulas are Eplc valid, namely the principle of quasi-explosion and the law of quasi-exclusive middle Eplc valid. Okay, let's move on to the next section entitled Main Theorems. In this section, we show the completeness, elimination, disability, embedding, negative symmetry elimination, contraposition elimination, and inversion elimination theorems, as well as self-extension property for Eplc. These are the soundness and completeness theorems with respect to the semantics for Eplc. The completeness theorem for Eplc is proved using Maillard's decomposition method that can simultaneously derive elimination and disability. Thus, we can simultaneously obtain the elimination and disability theorems for Eplc. Namely, the cut rule is admissible in cut-free Eplc, and Eplc is shown to be decidable. Next, we introduce a translation function for formulas of Eplc. Using this translation, we show some theorems for embedding Eplc into LK. We fix a set of proportion variable and define the set of new proportion variables. The language Eplc of Eplc is defined using phi conjunction, disjunction, implication, classical negation, paraconsistent negation, and conjunction. The language LLK of LK is defined using phi n, conjunction, disjunction, and negation. And mapping F from LEPLC to LK is defined inductively by the following clauses. In this mapping, negated proportion variable and conflated proportion variables are mapped into new proportion variables and negated new proportion variables, respectively. On the one hand, these conditions are straightforward. These conditions preserve the connectives under consideration. On the other hand, these conditions for negated formulas correspond to the De Morgan laws and the characteristic axiom scheme of Eplc. Also, these conditions for conflated formulas correspond to the axiom schemes for conflated conjunction, disjunction, and so on. Using the translation function, we can obtain a theorem for syntactically embedding Eplc into LK. Namely, relatively the mapping from Eplc to LK. Then we have the following condition. Namely, the secant gamma implies delta is probably Eplc or cut-free Eplc, if and only if the secant f gamma implies f delta is probably LK or cut-free LK, respectively. We can also obtain a theorem for semantically embedding Eplc into LK. Namely, relatively the mapping from Eplc to LK. Then we have the following condition. The secant gamma implies delta is Eplc valid, if and only if the secant f gamma implies f delta is LK valid. Using these syntactical and semantical embedding theorems, we can also obtain the elimination, completeness, and discernibility theorems for Eplc. Namely, we can obtain alternative embedding-based proofs of these theorems. This theorem is very important. This theorem represents a self-extension property for Eplc. The same theorem does not hold for typical paraconsistent logics, including Nelson's paraconsistent four-varied logic N4. This theorem is derived from the admissibility of the rules of contraposition and involution, which will be presented soon. We obtain the negative symmetry elimination theorem, which states the admissibility of the negative symmetry rules. This theorem is a characteristic theorem for Eplc. Based on this theorem, we can construct an alternative simple Gentzen-type secant calculus. We can construct the Eplc minus, which is regarded as a simple and compact alternative system for Eplc. Actually, Eplc and Eplc minus are theorem equivalent. The elimination theorem holds for Eplc minus. Thus, Eplc minus is regarded as a nice Gentzen-type secant calculus. Actually, these rules, initial secants and rules are derived, replaced with these four inference rules. This is a very simple system. We can also show the contraposition elimination theorem, which states the admissibility of the contraposition rule. This theorem is crucial because this theorem implies the self-extension property. The same theorem holds for Gentzen-type secant calculus A4 for SE4. The contraposition rule is not admissible in cut-free type secant calculi for Nelson's paraconsistent logic N4. Actually, this secant, where P and Q are distinct proportional variable, is a theorem for N4. But this action is not provable in this formula is not provable in N4. Thus, the self-extensional property also does not hold for N4. We can also show the inversion elimination theorem, which states the admissibility of the inversion rule. Then we can also obtain an alternative Gentzen-type secant calculus. Based on the contraposition and inversion elimination theorems, we can construct an alternative Gentzen-type secant system, Eplc asterisk, which is a theorem equivalent to Eplc. However, the elimination theorem does not hold for Eplc asterisk. This system is also very simple because these initial sequence and inference rules are replaced with only two inference rules. But elimination does not hold for this system. This figure represents a counterexample for the failure of the elimination theorem for Eplc asterisk. Namely, this secant is not probable in cut-free Eplc asterisk, but probable in Eplc asterisk with the use of a cut rule. This proof is an example of the proof. So far, we have explained the following contents. Especially, we have explained the system Eplc and its characteristic theorems. Then we conclude this talk and address future works. In this study, the extended paradefinite logic with classical negation, Eplc was introduced as a Gentzen-type secant calculus. This Eplc has connective conflation, paraconsistent negation, classical negation, and classical implication. Eplc is regarded as a modification of 4cc. Eplc is also regarded as an extension of BD plus and SE4. The completeness, elimination, and the dissolvability theorems for Eplc were proved. Eplc was shown to be embeddable into classical logic. The self-extension property and the admissibility of the rules of negative symmetry, contraposition, and inversion were shown for Eplc. Some alternative simple Gentzen-type secant calculi, which are theorem equivalent to Eplc, were obtained via these characteristic properties. Through the study of my paper on logical universals, I understand that SE4 is a good and interesting logic. Thus, I provide an interesting direction for future research on SE4. The main idea is to extend SE4 by adding the principle of explosion and the law of exclusive middle. Namely, this direction is explained as follows. To introduce some intermediate Gentzen-type secant calculi between A4 and LK. To consider some interesting and plausible Gentzen-type secant calculi, which are obtained from A4 by adding the principle of explosion and the law of exclusive middle. Actually, classical logic is obtained from SE4 by adding this principle and law. I recently found an interesting fact that a good cut-free Gentzen-type secant calculus for classical logic can be obtained from A4 by adding some characteristic rules. Actually, a new Gentzen-type secant calculus, FCL, for classical logic is naturally obtained from A4 by adding the following rules of explosion and exclusive middle. The system FCL implies that SE4 is a natural subsystem of classical logic. And these rules respectively correspond to the principle of explosion and the law of exclusive middle. Now, similar to the elimination theorem for LK, these rules are admissible in cut-free LK. Using this fact, we can show the equivalence between FCL and LK. Now, furthermore, we can show the elimination and contraposition elimination theorem for this system. While the cut rule in LK corresponds to the notion of consistency, the rule of explosion corresponds to the notion of paraconsistency, and the rule of exclusive middle corresponds to the notion of paracompleteness. Thus, these rules are crucial for characterizing these notions. I also found the following results on the elimination theorems for the related systems. The elimination theorems for these systems hold. A4 plus explosion is regarded as an extension of Cleane's strong three-byte logic K3, and A4 plus exclusive middle is regarded as an extension of the logical paradox LP. These calculi have not yet been extensively investigated. This figure represents the relationship among the logics. Here, FCL is the new sequent calculus for classical logic. FCL and LK are theorem equivalent. EK3 and ELP are the new logics that are obtained from A4 by adding the rule of explosion and the rule of exclusive middle, respectively. The contraposition elimination theorem cannot be shown for EK3 and ELP. Thus, perhaps the self-extension property does not hold for EK3 and ELP. I also provide another interesting direction for future research. I have an idea for extending A4 to the first order case. The intended future direction is as follows. To introduce a first order extension FA4 of A4, to prove the same theorems for FA4 as those for Eplc, to prove the Avron theorem for FA4. To prove this theorem, the contraposition elimination theorem for FA4 is required. Concerned with this idea, in my recent ongoing related work, I proved the elimination, completeness, embedding, and contraposition elimination theorem for FA4. The self-extension property holds for FA4, but the Avron theorem for FA4 has not yet been proved. By these fundamental theorems, I intend to provide a proof-theoretic justification for developing an FA4-based inconsistency tolerant automatic theorem proving that can simultaneously handle indefinite and definite information. I have also not yet introduced some temporal and modal extension of FA4 and A4. I intend to prove some characteristic theorems for these temporal and modal extensions. Thus, the intended future directions as follows. To introduce modal and temporal extensions of A4 and FA4. To prove some characteristic theorems for these modal and temporal extensions. To propose some realistic computer science applications of these extensions. Joint works are welcome. Thank you for your attention. Thank you.
Thank you very much.
Thank you.
So any question?
People also can use the chat, as Joylin was
Chat.
saying.
Thank you.
I have some question.
Yes, please.
Thank you, Professor Kamide, for your wonderful talk. I
you.
would like to know, when you presented your sequent calculus for Eplc,
Yes.
the axioms, you introduced the axioms in terms of variables, propositional variables.
Yes.
Yes, and then you proved that the axioms holds for formulas.
Yes.
And I want to know why you chose introduce the axiom in this way and not introduce the axioms in terms of formulas. Is there any technical problem?
Yes, technical reason. This can be extended to formulas because yes, this is a proportional variable, but this can be extended to any formulas. But this is a technical reason for proving embedding theorems. For to prove embedding theorem, we need this type of proportional variable initial sequence. This is just a technical reason.
Okay. And is there do you know if Eplc can be characterized by a matrix, by a logical matrix?
I don't know, but can such as a non-deterministic matrix. Perhaps Eplc can be characterized by matrix semantics, but I have not yet considered such.
Okay.
Yeah.
And my last question is about the you said that you prove completeness and cut elimination using Majara's method.
Yes.
And what's the difference between Majara's method and Schutte's method?
Yes, but very similar to Schutte's method, but Majara's method is only for proportional version.
Oh, okay.
And this is a very nice method for showing disadability. But Schutte's method is for first order case. Thus, disadability cannot be shown. But Majara's method is a proportional case and can be shown for disadability.
Okay, thank you very much, Professor.
Thank you. Thank you.
So I saw Professor Avron. I saw your icon. There's the mic symbol with mute. So would you like to say something? I mean, maybe try to test your mic. Okay, maybe, I'm not sure, maybe it's not working yet. So, and let's go on. And is there any other question? So maybe let me ask one. So I saw in your system you introduced, I'm sorry, I'm not familiar with that, but you have three things. One is the classical negation. The other is the Paraconsistent negation, and there's the conflation. And
conflation, yes.
Yeah, I like to know that. So for the rest, I mean, in your system, you have the implication and also the conjunction and disjunction in the classical way, right?
Yes, implication, conjunction, disjunction.
So what if what if we remove some of these connections? So maybe they'll be totally different. I mean, in your system, the classical implication and the
Yes.
classical conjunction addition is required. Is that the
Yes.
way? Okay.
Yes.
Mhm.
And EPLC is an extension of
Mhm.
classical logic.
Yes. Okay. I
Yes.
see.
Thank you.
So, any other question?
Criticisms are also welcome.
Yeah. So I have another question. So is there some corresponding, say, Hilbert proof system?
Yes.
I mean,
but perhaps
corresponding to your system, something like that.
yes, perhaps I can provide a Hilbert style system, but not considered here.
Yeah, I see.
Yeah. But not so difficult to obtain Hilbert style system. Perhaps.
Now, I have a question about the semantics of your system. Do you have any, I mean, we know that Ben-Abden logic is based on 4-valued semantics, but it's also possible to build a 2-valued semantics. I've been working on that because when we have a structural second calculus, it's always possible to give bivalent semantics. By the way, I wrote a paper with the bivalent semantics for the Ben-Lab project. So I guess your so this is your condition for bivalent semantic for the classical parts. But then
yes, this is a classical part. This is the same as the classical logic semantics.
Yeah.
Yes. Next, this is different from classical logic. This is a kind. This condition is Bell-Napton correspond to Bell-Napton logic for paraconsistent negation, and yes, this is different from Bell-Napton logic because conflation and interaction between conflation and classical negation condition. And this is also Bell-Napton, the same as the Bell-Napton logic condition.
But then when you are using T and F, it's only two values. Two
valued true and false.
Sorry?
Two valued semantics.
Two valued semantics. Okay, very good.
Yes. This semantics is based on two valued true and false, based on the set of classical truth values.
All right.
Only true and false is used in this semantics.
All right.
Yes. These conditions just correspond to these characteristic formulas of Eplc.
So I also have a question I would like to ask. So in your system, is there anything similar to Grebenko style theorem?
Grebenko style theorem?
Yeah.
Grebenko style theorem. I don't know. Grebenko theorem can be shown for this logic, but this logic is an extension of classical logic. Thus, perhaps some intuitionistic counterpart. If, but I don't know. But I did not investigate it. I didn't investigate the grouping theorem for this logic, but I'm sorry. I don't know. Yeah. But interesting direction. But
yes.
Interesting direction.
Yeah, I mean, I think treat this Eplc as a bigger one and try to see is there any sublogical bit they have something like Grabinko theorem. Yeah.
Intuitionistic counterpart of this logic is of course interesting.
So, is there any other question?
Maybe Arnon will ask a question on the chat, or is it too much complicated?
Sorry?
I'm saying that maybe Arnon would like to ask a question on the chat.
Chat. I'm sorry, but I don't. Chat.
I think he can type. I mean, with
okay.
Avron, I think if he like, he can type there, and you may answer. Yeah.
I still have problem with my own. Okay. I will send you an email for. Could you please send me an email for question?
Yeah, sure. If you want, you can put your email on the chat here.
Because as you know, I'm not good at speaking English. I'm very sorry.
Well,
that's all right. That's all right.
We succeed to understand you. You know, that's the important part.
But I now very interested in SE4, Avron's self-extension paradefinite logic. This is an extension of SE4, but SE4, I think SE4 is the essential interesting. I think SE4 is interesting logic, and self-extension properties most important, I think, most important properties, or the criteria of naturality of logic. Thus, I like to extend SE4. Okay. I'm busy with the X, which is taking place. Okay. Thank you.
You want to say one more thing, Junli?
No, I'm kind of running out of questions.
Oh my God. So I think we will start here for today. So thank you again to everybody, the speaker, the chair, and the two chairs, and all the participants. And next week, I mean, in exactly 1 week, August 10, we'll have a talk by another Japanese logician, Kenji Tokuo, sorry for my pronunciation, from the National Institute of Technology Japan, and then he will speak about quantum logic, and we'll have a presentation of a group of research group about quantum logic. So everybody is welcome to attend. Hope to see you next week. Thank you very much. Bye-bye.
Thank you very much.
Thank you. Bye.
Thank you, Sylvia. Thanks.
Thank you.
Thank you.
Bye.
Bye.